गुड मॉर्निंग बच्चों। आज हम ऑस्मोसिस और ऑस्मोटिक प्रेशर के बारे में डिस्कस करेंगे, बट उससे पहले थोड़ा सा जो लास्ट लेक्चर तक का फार्मूले को रिवाइज कर लेते हैं। जो हमने 4 कोलिगेटिव प्रॉपर्टी बताई थी, द फर्स्ट कोलिगेटिव प्रॉपर्टी वाज योर रिलेटिव लॉवरिंग ऑफ वेपर प्रेशर। उसमें हमने बोला था कि जो कोई भी अगर सॉल्यूशन है उसका वेपर प्रेशर उसके प्योर सॉल्वेंट के वेपर प्रेशर से डाउन आ जाता है, और P1 नॉट माइनस PS अपॉन P1 नॉट, वेयर P1 नॉट इज द वेपर प्रेशर ऑफ प्योर सॉल्वेंट, PS इज द वेपर प्रेशर ऑफ द सॉल्यूशन, एंड दिस इज कॉल्ड रिलेटिव लॉवरिंग ऑफ वेपर प्रेशर। और इसका फार्मूला था इक्वल टू X2, वेयर X2 इज द मोल फ्रैक्शन ऑफ द सोल्यूट डिजॉल्व्ड इन द सॉल्यूशन, दैट इज नॉन वोलेटाइल सोल्यूट। नंबर 2 हमने बोला था डेल्टा टी बॉइलिंग पॉइंट, दैट इज नथिंग बट मोलैलिटी ऑफ द सॉल्यूशन मल्टीप्लाइड बाई Kb, वेयर Kb was the ebullioscopic constant or the molar elevation constant. Number 3 delta Tf, that is the depression in freezing point, is molality of the solution multiplied by Kf, where Kf was the molar depression constant, or it is called cryoscopic constant. So Kb is called ebullioscopic constant and Kf is called cryoscopic constant, and both these constants depend on the nature of the solvent, like say water, or in whichever solvent we have dissolved the non-volatile solute, say they depend on the nature of the solvent. Say for water, we know that for water is Kb is around 0.52 Kelvin kg per mole. These values will be given to you, you need not remember, and Kf is 1.86 Kelvin kg per mole. So these 3 formula, and number 4 formula was osmotic pressure pi is equal to mRT, where m is the molarity of the solution and T is the temperature in Kelvin. So these 4 formulas we have already discussed, and today we take one example which was asked in the IIT main exams based on the depression in freezing point. After that we will discuss the osmotic pressure. So this numerical was they have asked the amount of ice the amount of ice that will separate out, amount of ice that will separate out on cooling a solution, on cooling a solution containing 50 gram of ethylene glycol. So there is a solution which contains 50 gram of ethylene glycol, and this solution is cooled to minus 9.3 degrees Celsius. Okay, and this is dissolved in 200 gram of water, and this solution is cooled to minus 9.3 degree Celsius, and Kf is given as 1.86 Kelvin kg per mole. This is for water. Now what we have to calculate is the amount of ice that will separate out, and 4 options were given. A is 38.71 gram, B is 38.71 mg, and C is 42 gram, and D is 42 milligram. So these are the four options. So how we will do? The formula is same, that is delta TF equal to molality into KF. Okay, now delta TF is given to us because this is cooled, solution is cooled to minus 9.3 degrees Celsius. So its delta TF we can say as 9.3 degrees Celsius. Okay, that is 0 minus 9.3, that is 9.3 degrees Celsius, and Kf is already given. So what we have to see is the molality. Now what is molality? Molality is nothing but the number of moles of solute per kg of the solvent. Okay, now number of moles of solute is known to us, that is 50 divided by molar mass of ethylene glycol, that is 62. Ethylene glycol is nothing but CH2OH, single bond CH2OH. So this is the number of moles of solute. Now what about the kg of solvent? Now it is given that it was initially dissolved in 50 gram. This 50 gram of ethylene glycol was dissolved in 200 gram of water. Now after the ice gets separate out, we will not have the same 200 gram of water, it will be less. So let it be, suppose x gram of ice gets separate out, then the remaining water will be, or the remaining this solution will be 200 minus x. So we can say the number of moles of solute per kg of solvent. So now the solvent is not 200 gram, it is 200 minus x, because x gram of ice has already been separated out. So this will be divided by 1000, so in kg, to convert into kg, and with this value of m I write this delta TF yani 9.3 is equal to m, small m is 50 by 62 upon 200 minus x by 1000, so it will 1000 will go upper side in the numerator, multiplied by Kf where 1.86. So we can solve this equation and find out x, and that value of x will come out to be 38.7 gram. So this will, A option will be correct, that is 38.7 gram. So that is how you can calculate the amount of ice that got separated from the solution. Now we take the chapter, this topic, that is osmosis. So first we show what do you mean by osmosis. So osmosis, as per the definition, is nothing but the movement of solvent molecules from solvent side to solution side. Okay, that is called osmosis. That is a natural phenomenon. Okay, so suppose I take two beakers. Okay, in this I have taken, say, pure solvent. So this is a pure solvent. It may be water, and in this side I have taken, here this 1 atmosphere pressure is acting, and here also 1 atmosphere pressure is acting over the surface. And now this is the, say, some solution which is having a non-volatile solute dissolved in it. It may be a salt solution or it may be any other solution. Okay, now if we connect these two solutions, these two beakers, by a like this, and with a semi-permeable membrane. This is called a semi-permeable membrane. What is the meaning of semi-permeable membrane? It is a membrane which allows only the solvent molecules to pass through. The pore size is sub-microscopic, so that only solvent molecules can pass through it. Solute molecule cannot pass through it. Okay, because solute molecule size is bigger. So what happens? due to this osmosis, these solvent molecules will pass from this side to this side. Okay. So this is called the osmosis. Now, if I want to stop this process of osmosis, I have to apply some extra pressure. Say pi. Pi is the extra pressure that is to be applied on the solution side. So that will prevent the movement of solvent molecules to pass through the semi-permeable membrane from solvent side to the solution side. Now, this pi, it was found experimentally that this pi is directly proportional to molarity of this solution. This solution is having say molarity m. What is molarity? Number of moles of solute per liter of the solution. And also this was found proportional to the temperature of the this solution or solvent. So we can say that pi is equal to mRT. This was found by experiments that osmotic pressure comes out to be mRT, where R is the ideal gas constant whose value is 0.082, that is bar liter per mole Kelvin, or we can also write the unit as liter atmosphere per mole or Kelvin, because 1 atmosphere is almost equal to 1 bar. So this is the formula. Okay, now if I want to do the reverse osmosis, then if I apply pressure higher than pi on the solution side, so reverse osmosis will start. That is used for the desalination of water, sea water. Suppose I take the sea water here, okay, and pure water here, then this reverse osmosis will make this sea water pure and pure water will come here. Okay, so that is the technique used for desalination of water, sea water, because in some countries there is no rain and the only source is the sea water. So there they apply this process for purification of water to make this desalinated water using the process of reverse osmosis. So they apply the pressure higher than the osmotic pressure on the sea water side, and the pure water is obtained on the other side. Now let us take some examples of osmosis. Like you know that 0.9% saline water it is called, which is nothing but 0.9% sodium chloride weight by volume. This solution of salt water is isotonic with our blood, because the blood also has the same osmotic pressure that is created by this solution of 0.9% NaCl. That is why this intravenously this 0.9% saline water is injected whenever somebody needs this loss of water, or if he has a dehydration, then this saline water is given intravenously, because this is isotonic with the blood. Suppose it is not isotonic, means it has the same osmotic pressure. Okay, if I use lower than this concentration, suppose the concentration is less of this saline water, then what will happen? This water will start moving from higher concentration to lower concentration. So if it is less than 0.9%, then water will start moving from lower concentration to higher concentration. Okay, that means our blood vessels or red blood cells will get swollen or they will swell, and if that is called the hypotonic. Hypotonic solution is one whose osmotic pressure is less. Okay, and if it is say more than 0.9% NaCl, then it is called hypertonic. And if I use intravenously this solution which is higher than this, then what will happen? Our red blood cells will get shrink, because water from the blood cells will start moving to the this solution side. So the red blood cells will get shrink. So that is why 0.9% exact saline water is used for intravenous injection. Okay. Now we will take few examples based on this osmotic pressure. So the first example is, and this osmotic pressure is used to find the molar mass of proteins, polymers and biomolecules. So how you will find this? How we find the molar mass? We have measure the osmotic pressure of a solution of this polymer. Suppose the polymer whose molar mass is to be found out, we dissolve that in a water and then or in any solvent, then we find out the osmotic pressure, and then this molarity is nothing but number of moles per unit volume of the solution. So this can be written as, what is number of moles? That is the mass, say W2 is the mass of solute dissolved, okay, divided by number of moles, so divided by molar mass, say M2 is the molar mass. So this is your number of moles upon volume of solution in liters, multiplied by R. R is nothing but 0.082 liter atmosphere per mole Kelvin, and temperature, say room temperature, say 298 Kelvin, suppose 25 degrees Celsius we use. Then with this formula we know the volume of solution in liters and the osmotic pressure we measure experimentally. Then what we can find out is M2, that is the molar mass of solute. Molar mass of solute can be found out by this formula. If we know the mass of the solute dissolved in V liters of the solution, then this formula will give the molar mass of the solute if we measure the osmotic pressure experimentally. So this method is used to determine the molar mass of some polymers or proteins or biomolecules, because this experiment can be done at room temperature, because these polymers and proteins, they get destroyed at higher temperature. So this is the most appropriate method to find the molar mass of various polymers, proteins or biomolecules. Now let us take one example. It is saying that calculate the osmotic pressure. Calculate the osmotic pressure of a solution prepared by dissolving 1 gram of a polymer of molar mass. So molar mass of polymer is given to us. Molar mass is 1,85,000. Because we know that polymers have a very large molar mass, and that is dissolved in 450 milliliter of water at 37 degrees Celsius. So what we have to find out is the osmotic pressure of this solution, and we have to find out in Pascal. that is Pascal is the pressure unit. Okay, so we will apply the same formula, that is pi equal to mRT, where m is the molarity. Okay, so R is the gas constant that we know. R is 0.082 bar liter per mole Kelvin. Okay, but in Pascal it will be 0.082 into 10 to the power 5 Pascal liter per mole Kelvin, because 1 bar is nothing but 10 to the power 5 Pascal. And temperature T is given to us, that is 272 plus 37, that is 310 Kelvin. So we know R, T and M is the molarity. So molarity will be how much? That we can calculate. Molarity is nothing but number of moles of solute. So mass given is 1 gram divided by 1,85,000. So that is the number of moles of the solute per liter of solution, that is 450 milliliters, so divided by 1000. So that is the molarity, and pi is also already given to this. Pi is to be calculated. So we know the molarity, we know the temperature and R. So what we can find out is pi, and this will come to around 30.5 Pascal. So this can be calculated. Okay, so that is the all about osmotic pressure and osmosis. If I ask you what is the difference between diffusion and osmosis, okay, what is the difference between diffusion and osmosis? So in case of diffusion, this suppose I take this two beakers. This is a high concentration solution, and this is a low concentration solution. So I have two solutions, one with higher concentration, means if say this is your M1, this molarity, and this is M2, then M1 is greater than M2. That I have taken the two solutions, and suppose they are connected. They are connected by say any membrane which is not semi-permeable. That means this membrane allows the both the molecules of solvent as well as solute to pass through it, because the pore size is not that small that it will allow only the solvent molecules. So now what will happen? Now suppose this is 1 atmosphere and this is 1 atmosphere. That means atmospheric pressure is acting on both the solutions. So what will happen? Because this membrane allows both the molecules of solute as well as the solvent, they can pass through this. So what will happen? The diffusion will take place, and diffusion will be from high concentration to low concentration. That means the solute molecules will pass through this membrane from, this is say number 1 solution and this is number 2 solution, from solution 1 side, from solution 1 to solution 2 side. So that is the diffusion, because the concentration of solution number 1 is higher than that of solution of this number 2. So these solute molecules will pass through this membrane from high concentration to low concentration. Now suppose I replace this membrane by a semi-permeable membrane. Now this membrane is a semi-permeable membrane. So what will happen? This will not allow the molecules of solute to pass through it. So there will be no diffusion from high concentration to low concentration. That was taking place when this membrane was a normal membrane. It was allowing both the molecules. Now in this case, as this membrane is a semi-permeable membrane, it is allowing only the molecules of solvent to pass through it. So the solvent molecules will now pass from this side to this side. Okay, now the flow of solvent molecules will be from this solution 2 towards solution 1. Why it is so? Because you see the concentration of the solute is higher here, but if we see the concentration of the solvent, that will be higher in this. Okay, so the solvent molecules will pass from 2 to 1, or we can say that the pi 1 will be greater than pi 2, because pi is directly proportional to molarity. So we can say that the solvent molecules will pass from a solution with low osmotic pressure to that of high osmotic pressure. Okay, so solvent molecules will pass, this pi 1 is greater because pi 1 is nothing but m1 RT and pi 2 is nothing but m2 RT. So because m1 is greater than m2, this is m1 here and this is m2. So pi 1 is greater than pi 2, and the solvent molecules are passing from this to this, that is from pi 2 to pi 1 side. That means from low osmotic pressure to higher osmotic pressure. So movement of solvent molecules takes place from lower osmotic pressure to higher osmotic pressure solution, or from hypotonic to hypertonic solution, or from dilute solution to concentrated solution. So the movement of solvent molecules is always from low concentration solution to higher concentration solution. Okay, that is the osmosis. That is why we see that when we use salt water, then no bacteria can develop. Suppose in the pickles or meat is preserved with salt water. Why? Because any bacteria develops, that will get dehydrated, and this water from the bacteria or some say fungus will pass to the salt water side, because salt water is higher concentration. So water will move from low concentration to high concentration. So we can say that no bacteria will develop, they will die as soon as they grow. So growth of bacteria will not be there if we use salt as the preservative. Okay, so this is how the concept of osmosis is there. With this we conclude our today's session. Next session we will take Van-Hoff factor, and this whole chapter of solution will be complete, and after that only one chapter, that will be the Henry's law. So Henry's law and Van-Hoff factor, that both we will take in the next session. Till then, thank you, all the best.